So I asked Bugmeat for the privilege of announcing the next speaker. Bugmeat, I think, has been doing a fantastic job in this room all day. I'll pass this back to him for Q&A. But I just want to say it is my absolute pleasure to announce our next speaker, Saul. This is, I believe, Saul's 4th PyData conference. His first talk was at PyData Boston with me, and then we did New York, then Silicon Valley, and now Berlin. So I think we owe him a big round of applause. You know, he's one of the regulars, and if you come to PyData in New York this fall, I'm sure he'll be there too.
That's okay. Thanks, James. Okay, so speed without drag. First of all, if I learned something from James Powell here, is that you can't ever talk too much about yourself. So I'll talk a bit about me first. I am a Spaniard in New York. The song's not the same, it's a bit crappier, but the accent's better. I had to resort to musical jokes because the soccer jokes I had turned on me this year. But at least I'm not Brazilian. My background is in electronics and CS as well. And I've been doing Python for 4 years now. First in ad tech, at Ampush, doing Facebook advertising. Sort of saltless work, but really interesting technically. And then at Thinkful, teaching people how to code, how to build websites and apps, which is much more fun. You can contact me at that email address. You can tweet at me at definitely. And you can go to GitHub if you want the slides, the IPython notebook that's behind this reveal.js slides. So what's the story? What are we talking about today? The story for this is, I don't know about you guys, but I really like Python. If I have to write code, James likes Python too. If I have to write code, I much rather write Python than anything else. So, you know, every now and then you bump into someone that says, "Oh, you can't do that in Python. Python's just too slow." Who here has heard that before? Yeah. Who here has reacted to that quite aggressively? Okay, by the end of this, I hope you leave this place with enough information to react aggressively to that stage. So the story is basically some other engineer that probably likes JavaScript, they all like JavaScript, telling you how slow Python is and how crappy Python is. And that's what we will try to counter-argument. And in particular, we're going to talk about numerical Python code, because that's what PyData is all about, right? When we really, how to speed that numerical Python when we really don't want to waste time, or we don't want to write Cython or C modules or stuff like that. But before, now that I kind of packed your interest, hopefully, I'm going to tell you not to do it. I'm going to tell you to think first, because there ain't no such thing as a free lunch, and there ain't no such thing as a free speed up. You're going to have deployment problems, maybe. You're going to have overhead to onboard other engineers into your project. You're going to have all these problems if you use some of the tools we'll present today. So think first, and you know, if you can get away with it, just don't do it. Don't even try it. What if instead you think things through and refactor? Maybe you can do that. Or, you know, this is Jeff Bezos' most favorite way of solving things. You just throw money at the problem. You buy more servers, you basically waste resources. You can also evaluate other things you could be doing in the time it will take you to implement these things. And you can also limit on the GIL, Van Rossum switches to Java. Well, we're going to skip that part because I want to come back here next year. All right, so what are we doing here? How do we speed Python up? But then again, let's think first on other ways of not using these tools, these libraries. Before we go and try to use numExpert on something, we have to figure out if we have an I/O problem somewhere, if we were serializing or serializing somewhere else. If we have any other bottleneck that's not computational, this stuff won't help you. So figure that out first. Make sure your code's not doing stupid things, such as calculating something over and over. Some developer that I might or might not know, or might not be, was compiling our regex repeatedly not too long ago. So try not to do those things. Are you discarding any computation? Meaning, don't calculate precision if you're not going to use it. If you're going to floor a number, don't calculate the entire thing. Different types of randoms have different speeds. How much entropy do you really need? Many other things. There's a link here to a talk by David Schachta. That's a good one to say here. Schachta, I think. He's a lead engineer at Disney. He gave a really good talk last year on how to speed up some problems. Different kind of focus. His focus is actually do the legwork that the old timers, I guess, kind of did, but definitely interesting to watch. And then, of course, in CPython, capture the low-hanging fruit. Try to use multiprocessing. Take into account the overhead and Amdahl's law, which is really present in Python, as you know. Use immutable objects if you can. Careful with temporary values. Try to use things that we don't use in Python, like slots, fast append comprehensions, generators. But if you use generators, don't use his code. But again, this is not the point of the talk. It's a Python conference, so we're going to talk about how to do PyData solutions to this problem. So we're going to go through a list of libraries and tools that will help you circumvent, quote unquote, the safety of Python. Because in reality, what we're doing when we are speeding things up is either jumping out of Python altogether, whether or not we're actually doing the work ourselves. If you're using NumPy, you're basically using someone else wrote in C, right? Or Fortran. So for that, we have many tools, such speed. It's amazing, this talk was written in February of this year, and the memes are already outdated. But anyway, we've talked about exhausting CPython. We will go over NumPy, Numba, Parakeet, numExpert, Theano, PyPy, NumPyPy, Cython, Blaze, Pyston, and Python. And to do that, and to make it slightly less boring, we're going to use a driving example, which is one of my favorite interview questions, which is building a function that calculates the area of a polygon given its coordinates. Nothing too crazy. And before we get down to it finally, first a disclaimer, we're going to be doing a lot of time edit and a lot of timer stuff. There's value in the measurements, but they're not gospel, they're biased. The problem itself, the driving example, is what it is. So it's obviously as I say, reductionistic tool to figure out which works and what doesn't. Which means some of the tools in the libraries might not do that well for this particular problem. That doesn't mean they're not valuable. That just means that they're not the best tool for this particular problem. And of course, again, we just have one benchmark, so don't focus too much on the numbers. With that, I'll show you how I solved my own interview question, which is something as terrible as that. This is a diagonal polygon generator, which will basically generate coordinates that for a polygon that looks kind of like that diagonal we have up there. The code is terrifying, really. I don't like it at all, but it does the job. When you write code as ugly and weirdly looking at this, if you're James Powell, you make it a presentation and tell people not to use it. If you're me, you test it and you call it production ready. So that's what we're going to do. And then there's the solution to the actual math problem, underlying math problem, which is basically getting the sum of halves of all the 2x2 subdeterminants in the coordinates. This is basically the shoelace formula for those interested, which is basically a corner case of Green's theorem, which in turn is a subset of Stokes' theorem. Basically what we're doing is multiplying coordinates x0 times y1 and that, so nothing too crazy. Anyway, it's tested too, and this looks somewhat better, so we're going to go with this. And if we create a diagonal polygon that's 200,000 levels tall, and we run that solution, we get half a second, or 1/4 of a second in time it in IPython. So there's that. The first thing I talked about was CyPy. CyPy, as you know, it's a stack, it's an ecosystem. It has things as amazing as IPython, NumPy, PyTables, lots of things. And then it's its own library, the own original CyPy library. In CyPy, we basically have NumPy, which, as you know, it's the n-dimensional array implementation that's basically part of CyPy, but it's also its own thing. So what happens if we try to use NumPy to solve this problem? Here the only thing we do is we create a polygon that's, we translate those coordinates into a NumPy array. And then the NumPy solution for this is basically the same. We're using the same formula, only we're using vectors and we're using vector operations directly. Just by doing that, we have, well, we go from, yeah, what's that, like 30, 25x improvement. So that's pretty good, and we really didn't do anything. Next comes Numba. Numba, some of you might know, is a just-in-time compiler that leverages LLVM and translates a subset of Python into LLVM IR to further leverage the LLVM compiler and just-in-time switch your code for that binary bytecode, I guess. There's experimental support for CUDA, static compilation, and then multi-core and GPU support. That's a freemium model, I guess. It's made by the Continuum guys that are around here, so if you have any questions about it, I'm sure they'll be happy to talk about it. As James was saying, we gave a talk in Boston about Numba. So if you're not already tired of me, you can go online and watch that one too. So Numba has a really simple API. It's basically a turnkey solution where you don't have to do anything if you don't want to. The only thing you do is either decorate the function you want to speed up, or wrap it in Numba's JIT, and you have your Numba function. And just by doing that, sometimes you get speedups. In this case, the naive Python solution does slightly worse, and the NumPy version gets slightly improved, but not by much. That is not to say that NumPy is worthless, far from it. You can find examples online of Numba doing 1500x improvement in some algorithms. Just didn't work in this case. Unrelated to our driving example, I wanted to show you something else that Numba does that's pretty powerful, which is vectorizing functions. You can create a function the same way you can vectorize a function in NumPy to apply using broadcasting to a vector. You can do it as well with Numba, only NumPy's vectorize was never supposed to be for speed. It was just basically a nicety, a helper. Numba's vectorize will speed up things a lot. In this case, we see how multiplying something by itself and adding one gets sped up a lot, 40x. And the benchmark with NumPy is close, but you gotta realize that NumPy square is optimized, and this is a really simple function I chose for the example. As soon as you start doing something more complicated, NumPy won't probably be able to follow the Numba vectorized function. So there's that. That's pretty interesting. Next up is Parakeet. Parakeet was originally pretty similar to Numba in goals, although the implementation was pretty different. As of late, it has taken a turn. They basically deprecated the LLVM backend and are focusing on C and OpenMP. And they are also implementing some functions manually, so it's less about inference and more about actual optimization of certain things. Experimental support for CUDA as well. I haven't tried that, so can speak about that. But for our driving example, the API is exactly the same or fairly similar to Numba's. And it's sort of the same thing with the naive Python version, which doesn't work. I assume it's all the array access. But for the NumPy version, we get a speed up. So we go from an original figure of 9 milliseconds for NumPy down to 1.2, 1.3. So that's pretty good. And again, we did nothing. NumExpert, Francesc Alted, my fellow countryman, is here, and he gave a talk earlier in this same track that included NumExpert. But for those of you who missed it, NumExpert is a library that helps you optimize the way vectors go into the processor, breaks them down into the same size as the cache, so that everything's used up in the best way possible. It avoids intermediate values, so less storage used, and thus you get speed improvements. And then there's support for OpenMP and the vector math library and the math kernel, Intel's low-level implementations. It's a reduced set of instructions. It's a Python. You have to. It looks like Python, but it's basically a set of expressions that are evaluated. But it's highly performant. In our case, other than getting the columns of the matrixing separately. The only thing we do is we define again the vectorized operation, and when we evaluate it, we go from again 9 milliseconds in NumPy to 2.5. So that's close to 4x for little work. I also suspect that as we're using 200,000 levels for that polygon, I also suspect that the more that grows, the bigger the improvement will be. Another great tool, really complex, is Theano. It's mostly for array computation on GPUs, so in our case we won't see that much improvement, but it has support for CUDA, native optimization. It's a project that's been in the works for a long time, and it's fairly complex and serious. In our case, we're just not leveraging it as much. It has some tricky dependencies because it's, again, the GPU and the CUDA stuff are kind of tricky. Anaconda will solve it if you want to play with it. That's how I recommend you install it. You can't see it here, but there are, next to this slide, there are a couple things I had to do to actually get it working on IPython 2, but they are heading on reveal. In any case, we defined the vectors and the operation as well, and then we call it. So pretty much the same thing. Although you can tell by the syntax here that this is a much more array GPU oriented solution. In any case, we go up to 40 milliseconds, which is 4 times what NumPy was giving us, and much worse than NumExpert. But you got to take into account that this is still much better than CPython, the naive solution, and that with a larger data set and with CUDA, this would look much different. And next comes PyPy. We're here leaving the CPython world. PyPy, as you might know, it's a just-in-time compiler following the Python spec that is not related to CPython at all. What that means is that things that work in CPython don't necessarily work in PyPy, as we will see. It lacks support for some things, but it's a really mature project and it's highly compatible. And what we're doing here is basically running that same code in the shell. I don't know if there's a PyPy backend for IPython, but I chose the easy way out, which is running it on my shell. And what that means also is that numbers can't really be compared to what we've been seeing inside the IPython notebook, because timeit is different from timeit.timer. So we're only able to compare PyPy with Cython and with CPython, with the shell version of CPython. In any case, it's the same code, it's the same size of diagonal polygon, and we get 30 milliseconds. Whereas if we run Python, we get 2.5 seconds. So PyPy is much faster. Now, there's also NumPy for PyPy. It's called NumPyPy. It's a fork of the original to make it work. You can go to that URL. It's not there yet, and what that means is that there are things that are missing. You can go to this URL and see what's supported and what's not. But in any case, for our example, it works. But the truth is, if we run it, we find that it's 10x more than 10x slower than just the PyPy version. So I guess the takeaway is NumPyPy is a work in progress that will let you use your NumPy code inside PyPy, but it's not necessarily faster, at least not for this example. I'm sure you can come up with an example where it will actually be as fast or faster than the regular NumPy. And for comparison, we run the same script on CPython, and CPython is fairly slow, and NumPy over CPython is almost as fast as the naive version on PyPy. Again, as I was saying, time it, percent time it inside IPython. It's great. If you don't use it, I recommend it. But it's also written, implemented in a way that you can't really use it outside IPython, so I had to resort to using timer. And what that means is that the measurements, not that they were too reliable to begin with, but as soon as we start doing this, the measurements are completely off from the IPython notebook. Cython is, as you can probably tell, Python on the JVM. It needs the JDK to install it. And when we run the very same script we were running earlier, we get 2 seconds, which is slightly less than CPython, but obviously much worse than PyPy, NumPy, and the rest. And there is no NumPy for Cython. You can find something called numerical, I think. I don't know if it's maintained. The people behind, the person behind Cython was originally the person that wrote numeric, or one of the, not numeric, but numerical, I guess. The original Python one. But I hear they have moved on to .NET, if I'm not mistaken. Anyway, no NumPy for Cython. There's definitely a use case for Python on the JVM. It looks like it's fairly similar in performance as CPython. If you are okay with the JVM startup time, which is not included in this figure. Finally, for the scripts we ran on the shell, we've got the ranking. It's Python, then Cython, NumPyPy, NumPy, and finally PyPy. It's the fastest. Other stuff that we won't see how it performs, but that's looming and will be around in the future, hopefully, is Pyston. Pyston is a new implementation of complete standalone implementation of Python, being driven by Dropbox. It's a just-in-time compiler. It's built on top of LLVM. So it's pretty similar to Numba's and Parakeet's original approach, only they're not choosing to do it for the numerical set of instructions, but rather for the entire language. Of course, that's a huge undertaking, one that only a company that size could tackle. This is really, really early, so we'll see where that goes, but it's really promising. We've got Blaze. Travis Oliphant gave a talk earlier on this track about Blaze, so I wouldn't go too much into it, but it's also one of the hopes for Python and for the future. LLVM is in the mix there as well. And then Python, which is C++, modern C++ transpiler. So it transpiles a subset of CPython, subset of Python actually probably CPython, to modern C++ through annotations, which is fairly simple, as long as the stuff you're using is supported. Has support for multi-core and SIMD instructions, and it does a fair amount of AST optimization and parsing, but it doesn't use a common backend such as LLVM. They have chosen to write their own optimizations. There was a talk given by one of the main committers at PyData Silicon Valley. I recommend you watch it if you're interested. This is kind of what it looks like. So you write your code, and then you prepend your function with a comment that will be parsed by the transpiler. And when all else fails, you run away, or you use C extensions, Cython, C-type, CFFI, anything but leaving Python. Do not leave Python. And to recap, it's not free, so try to avoid it. Think first. And use the best tool for the job. There's a lot of libraries and tools that you can use, and it's testament to the maturity of the Python community and in some way the ingenuity of the community. So try to leverage those if you can, so you can keep using the second best tool for any job, which is, of course, Python. Thank you.
So have you compared this against doing inline NumPy expressions?
Sorry?
So, I mean, in-place NumPy expressions. So the way you wrote it in NumPy, you do like three or four copies, but you can easily write it so it doesn't do any copies by using in-place operations. So have you compared against that?
Have I compared?
Like, how fast would it be compared? Like, if you write it in NumPy, so it doesn't make any array copies.
Let's see. So.
And you wrote it down in NumPy in a naive way.
Yeah, you were saying here, don't create the.
Yeah, don't create so many temporaries.
Yeah, probably faster. Yeah.
Yeah. So the question is, but you haven't compared this to how much faster the other versions are.
No, I have not.
And the second question was, so have you done it in Cython and?
Cython, no.
Okay.
The whole goal was to not leave Python. If you write it in Cython, it's going to be much faster. Like especially this problem, it's so that simple that it's going to fly. But then you're writing Cython.
But the question would be like, how much of this do you lose by not going out of Python?
Probably a fair amount. I had it. I don't have it in this laptop, but I had it running in pure C. And I remember it was fairly faster in C. It was at least 1 or 2 orders of magnitude faster than the, I guess, naive NumPy implementation. So obviously much faster, but then you have to tell the intern what Cython is or what C is, right?
Do you know if there are any projects that aim to combine these two hot IDs like Cython and JITs? So use Cython maybe as a backend for just-in-time compiler? Because you could infer that, right? If you add some type annotations in signatures, which you do with Numba and apparently with other tools, would it be imaginable to have some type inference and then compile the Cython on the fly?
So the question is there a library that leverages all the type inference there's already in some of these libraries to generate Cython instead of? I'm not aware of one. I guess it's an idea someone could entertain.
Cython promise.
Sorry?
They want to add it more to
Cython tries. Well, yeah, that's true. The latest versions of Cython claim that you don't necessarily have to annotate everything. Python does something close to that, so Python would be like a pretty good candidate to do something like that. But I'm not aware of something that's already out there.
So I have a kind of long question, which is, in my opinion, optimization is kind of an operational process. Like for this problem, the mathematician looks at the Platonic ideal for the formula, and that's all he cares about. But it's the practitioner, the data scientist, who needs his answers tonight, who has that requirement for speed. He's actually running code to produce results. And what I'm curious about is the way that it seems like people write code is you have some requirements, you write code, then you optimize it, then the requirements change, you change the code, then you re-optimize it. And it seems like some of these approaches are more flexible than others. Like num expression you showed seems to only support a certain number of operations. So could you comment on which of these approaches might be more flexible in the long run? Because you wouldn't want to spend 20 hours with Numba, only have to throw it away if the problem changes a little bit, right?
Yeah, definitely. So as I said at the very beginning, think first, try to avoid these things, because anything you add to your code, any code you write, the best code is the one you don't write. Once you start writing code and adding libraries and adding things, that automatically becomes a liability in terms of code-based management. I would say that if you're worried about that, the best tools are the ones that are, annotate your code and let you not do anything else, such as Numba or Parakeet. If you suspect that your problem will change in definition, but not by much, it's probably safe to say that most tools will react the same way. If you hit a sudden change of direction, of scope, something where you actually need to change things dramatically, it's safer to be CPython only and not, if you threw money at the problem like Bezos wanted, you're good to go. If you've been using Theano and have like weird tensors written, and Theano doesn't support the next thing you need, you're going to be in trouble. So definitely try not to do it, period. And if you do it, try to stay as close as Python as possible.
I have one more follow-up question. So from this operational perspective, you might sit down and say, I have 5 hours to make my code faster, and I have to pick a particular approach. And we saw different results with different techniques. Like Numba didn't really help that much here, but you said it helped a lot in other circumstances.
Yeah.
Do you think that there's the same variance for outcomes for each of the approaches, or do you think that one of these techniques might give you some speed, some guaranteed speed up, but not that much, and other approaches might either give you a lot of speed up or no speed up whatsoever? And you could use that to guide, how you spend your time.
Yeah, I think there's definitely a lot of variance, and that basically is encoded in the type of problem, in the type of data, in the type of computation. And you probably can't escape that with these tools, because most of them are really specialized and fairly mature, but really siloed. So yeah, once you decide you want to do this, the best way of not working too much is by trying a bunch of them, seeing what works for you, seeing what you want to do, because PyPy might be really fast, but I don't want to deploy PyPy on production because it's a different language, quote unquote. So yeah, definitely a lot of variance and a lot of difference depending on what problem you're trying to tackle. What's my favorite? Put me on the spot, huh? I really like numexpr. I think it's really smart and I think it's really fast. numexpr.
Any further questions? Okay, in that case, in about 10 minutes, we meet in the other room for the panel discussion. And let's thank our speaker once more.